Hi there, how's it going? Welcome back to another session of Brain Training, a place where I train my English by explaining LeetCode solutions. And today we are back again with the LeetCode 912 sorted an array, a question that asks us to rearrange the items within an integer array such that they appear from the smallest to the largest. This question also has a acceptance criteria regarding the time complexity. We should come up with an algorithm that runs an O n log n time complexity. But we're not going to be able to accomplish this just yet because the algorithm we're going to be writing, selection sort, runs an O n squared time complexity. Today our goal is to enhance the performance of our previous attempt, which used bubble sort. So without further ado, let's dive right in. Just like bubble sort, selection sort also will iterate over the array multiple times, meaning we're going to have multiple passes. The main difference here is that instead of shifting the largest item to the end of the array, we're going to find the smallest item and place it at the beginning of the array in each pass. So let's go to an example to see how that works. Over here we have the initial setup for the first pass of selection sort. We're gonna need three variables this time. The first one is the outer loop variable to keep track of how many passes we're going to have in this sorting process. The second one is the inner loop variable to keep track of the index of the item we're looking at during each iteration. Last but not least, we have this variable to hold the index of the smallest item we have seen so far during the iterations. At the beginning of each pass, iOS always starts at the same position of our outer loop counter, which means that the smallest item we have seen so far is 5. And the inner loop variable always going to be a step ahead, which makes it possible to compare adjacent values. On each iteration, we'll check whether the item at J is smaller than the item at iOS. If so, we're going to update the index of the smallest item. And for the first iteration, that condition is true. So we're going to update iOS with J and move to the next iteration. On the second iteration, that condition is false. So we'll keep going. And the next and last iteration, the condition is true. So we're going to update the index of the smallest item. At this point, the very last iteration is the only time we're going to swap elements. And this is how we gain performance compared to bubble sort, which also means that we're going to move the smallest item we have found to the lowest index available. In this case, we're going to move 1 to position 0. And that's all for the first pass. Quick FYI, it's a new day. I had to pause the recording for a while, but I'm back now. So let's jump into the second pass. For the second pass, we start at position 1 because this is the next lowest available index. iOS also will be placed in the same position, and J will be placed at the next adjacent number. So now we're going to check whether 3 is less than 2. It is not. So we do nothing and move to the next iteration. Is 5 less than 2? It is not. So no swap requires here. We are good to move straight to the next pass. And for the last final pass, we just have to compare the two last adjacent numbers. So is 5 less than 3? It is not. So we are done. The entire array is sorted and no swap requires here as well. We are good. We're good to move to the code. So without further ado, let's jump into the code. We'll begin with the outer loop, which is responsible for controlling the number of passes through the array. And to avoid getting out of bound, we'll use this -1. We don't need to go the last pass. And then we're going to initialize the variable that will hold the index of the smallest item and initialize it with the lowest available index. Next, we declare the outer loop, which is responsible for the iterations and comparisons, and always start one step ahead, so I plus 1, going all the way to the end. And inside the inner loop, we just check whether or not we find a smaller item. If so, we just update our current index. That's all for the inner loop. And after that, we just check whether or not we should swap elements. If so, we just use the standard swap technique. This is all we need. And finally, we are good to return the sorted array. Let's submit this and see what we got. And time limit exceeded. Yeah, we almost got it. We made it up to the 19th test case. So we are close. we are close. Let me zoom out a little bit. Regarding time complexity, we still have the O(n) square, the same as bubble sort, but as you can see, it's more efficient because in the bubble sort implementation, we got up to the 16th test case, if I'm not mistaken, but that's a huge improvement right there. But it's still the same big O notation. For space complexity, it's the same. We don't need extra space. It's O(n). I give selection sort a 6 out of 10 score because it doesn't feel as good to write as bubble sort. That's all what I got. Even though it's a more performant solution, doesn't look good, it doesn't feel good as bubble sort because you have this variable here and this check over here. I don't know. Bubble sort, you do everything inside the inner loop, so it's more concise, more elegant, if you will. That's all I got. Thanks for watching. See you in the next one. We are getting there. We are getting there.